Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click that subscribe button. That said, let's get into the current video. Okay, so I'm going to talk about the derivative of the sine function, and I'm going to do it in three ways. The first way I'm going to do it is graphically. The second way that I'm going to do it is using the definition of the derivative. And the third way that I'm going to do it is using the Taylor series of the function. And so what I'm going to do is present the derivative of the sine function, but I'm going to do it in three different levels of sophistication. Starting with the most basic, looking at the graphical interpretation, then we'll look at the definition of the derivative and how that applies to the sine function, and third, we'll use the Taylor series. Now, depending on where you are as a student, if you are let's say a beginning pre-calc student, you should be able to roughly understand the graphical interpretation. If you're a beginning Calc 1 student, the definition of the derivative should be familiar to you or should make sense. And third, if you are a Calc 2 student, meaning you're more than likely at the end of your Calc 2 class or beyond, the Taylor series representation should make sense to you. But regardless, there should be a little bit that we can get out of all three of these. Let's go ahead and run through it. First and foremost, let's look at the graphical interpretation. So let me go ahead and section this off. So first and foremost, we're going to do this graphically. Let's look at the graph of the sine function. So the sine function looks like the following. Okay, where of course the intercepts occur at 0 and pi and 2 pi, so on and so forth. Now this is the graph of f of x is equal to sine of x. And what I want to do is I want to use this to come up with a graph of the derivative of the function, whatever the derivative is of this. So coming down here, I'll label this as f prime of x. Now, remember what the derivative does. The function values for a derivative gives me the values of the slope. Well, in particular, we can pinpoint the value of the slope, let's say, at the top and bottom of each one of these hills and valleys. Of course, the slope there is 0. So the function value for the derivative would be 0 at those points. And again, remember the intercepts for the sine function was 0, say, to pi. So this being right in the middle, this would be pi over 2, and this would be 3 pi over 2, etc. All right, let's look at a couple other points. At the origin, the slope here looks like it's 1. So that means the function value at the origin is going to be 1. The slope here at pi is, well, that slope of that tangent line is actually -1. So that means that's going to give me a -1. And we could continue this farther and farther out, just until we kind of see what the pattern is. Down here, again, at the bottom of this valley, that has a horizontal tangent, right? So that means that the slope is 0, so the derivative value there would be 0. And let's go ahead and let's stop there. Now, sine of x is a differentiable function, meaning its derivative is also continuous. And what we now have is the derivative, whatever it is going to be a continuous function that passes through those points. Well, what sort of a function can we generate that passes through those points? Let's come up with one. Let's say I graph the following. And since the sine function is periodic with period 2 pi, that pattern continues to repeat itself. So it makes sense that the slopes would also repeat themselves. And that would give me something like the following. And of course, that's going to continue in both directions. Now, what sort of a function can you think of that has the same exact shape as the sine function, but is just shifted pi over 2 units to the left in this case. What could that be? Well, think about that. All right, now let's look at the definition of the derivative. So let's use the second representation here. And this one will actually tell you what the derivative is, and you should be able to guess based on that picture. Okay, so the definition of the derivative, remember, is the limit of the difference quotient. That says that the derivative, again, here's the general formula, right? It's the limit of the difference quotient okay, so limit of the difference quotient. And then if I apply that difference quotient to the sine function, we get the following. The limit h goes to 0 of the sine of x plus h minus the sine of x. And again, all over h. Now, when we take a limit, the first thing we ask ourselves is, can I plug in the value that this variable is approaching? And if I do, I go ahead and do that and do the computations, right? But if I can't, then we have to do some sort of manipulation or some sort of work so that I can hopefully plug that value in. Well, I can't do anything as far as like a conjugate or expanding. Sine's not a linear function, so I can't separate that. But look what I have. I've got a sum of two values inside the sine function. That should remind you of a trig identity, the sine of a sum of two angles. Okay, so let's go ahead and expand that. So this gives me the limit as h goes to 0. And I'm just going to go ahead and write the identity for the sine of the sum of two angles. So it's going to be the sine of the first angle, and then it is the cosine of the second, minus, hopefully I have enough room here, this would be the sine of the second angle, cosine of the first, and then I guess I'm going to have to squeeze this in here, so I'm just going to say minus sine of x. And then it's that whole thing over h. So kind of ran out of room on the screen there, so this all should be on the same line. So down here, let me kind of scooch this over a little bit. So this would be equal to the limit as h approaches 0. Now I have to figure out a way to work with this. Now if I look at these terms, I can see that the first and the last have a sine of x that I could factor out. So let's go ahead and factor that out. So I have sine of x times, well, cosine of h minus 1. And then it looks like I have minus sine of h cosine of x all over, looks like my marker's running out here, all over h. Now, let me see. Oh, going back up here, the sine of the sum of two angles, the sine stays the same. So that should have been a plus. That should have been a plus right there. And then that means that down here, this would be a plus. Okay. Now, let's separate, well, let's look at what we have here. I've got I can separate the fraction. Let's do that in this line right here. So all I have to do is let's break that fraction bar, and then let's put an h over this. So we'll just separate the fraction. And let's scooch this guy over a little bit. Okay, now remember we're taking the limit as h goes to 0. So in that computation, x is then a constant with respect to h. We only look at h going to 0. Now, sine of h over h as h goes to 0, this is actually a fairly common limit that you will learn in your Calc 1 class, and that ratio converges to 1. Okay, and moreover, this other expression over here, this is also a common limit that you will learn, cosine of h minus 1 over h, and that goes to 0. So therefore, this is equal to sine of x times 0 plus 1 times the cosine of x, which gives me, of course, the cosine of x. So that tells me that the derivative of the sine function is the cosine function. Well, if I go back over here to this graphical representation, that makes complete sense now because this is the graph of the cosine function. And we saw that graphically, and then now we saw it using the definition of the derivative. And this is a similar computation that you would do about a month into your Calc 1 class, okay? Now what I want to do is let's do one more level of sophistication. Let's ramp it up just a little bit to what you do at the end of a Calc 2 class, and let's look at the Taylor series representation of finding the derivative. Okay, so for the Taylor series, again, if you're in Calc 1, you're not going to know what I'm talking about in this next part here, but I wanted to kind of show this for a variety of audiences. So therefore, the derivative of the sine function using the Taylor series representation goes as follows. The derivative of the sine function is equal to, so it's the derivative, and what I'm going to do is I'm going to replace the expression for the sine function with its Taylor series, more specifically the Maclaurin series representation, which is the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So that is the Taylor series representation of the sine function, okay? So now to differentiate this, what I'm going to do is I'm going to expand this out as follows. This is equal to the derivative of, so let's write the first handful of terms. If I plug in 0, -1 to the 0 is 1, and then x to the 2n plus 1 would be x, and then the denominator here would be 1 factorial, so in other words, it would be x. And then if I plug in n equal to 1, I would have a negative, and then x to the 2n plus 1 would be x to the third, and then the denominator would be 3 factorial. And then if I plug in 2, this would be plus x to the fifth over 5 factorial. And then minus, plug in the next, this would be n equals 0, 1, 2. So if I plug in n equal to 3, it'd be negative, and it'd be x to the seventh over 7 factorial, so on and so forth. So we can see that there are alternating signs. The exponents on x are the odd integers starting with 1, and the denominator is the factorial of the exponent. Okay, now what's nice about this is I can actually do term-by-term differentiation. So I can use the power rule repeatedly. If I differentiate this, I'm going to get 1 minus, so the power rule applied to this second term here, of course, the 3 comes down, but then 3 over 3 factorial, the 3's cancel, leaving a 2 factorial, which makes this an x squared over 2 factorial. And then plus, for this third term, the 5 comes down, 5 over 5 factorial, the factors of 5 cancel, leaving a 4 factorial. So I get x to the fourth over 4 factorial. And then let's just do one more. This next term here, the fourth term, the 7 comes down, canceling with the 7 and the factorial, leaving minus x to the sixth over 6 factorial, and again, so on and so forth. Now, sine function, remember, is an odd function, which has all the odd powers in its Taylor series. And the cosine function, being an even function, has all of the even powers in its Taylor series. This is, in fact, the Taylor series for the cosine function, which once again demonstrates the fact that when I differentiate the sine function, I get the cosine function. Okay, so now you've seen it 3 different ways. Hopefully at least one of those makes sense to you. Hopefully all of them do, but if not, hopefully at least one kind of provided a little bit of an insight as to why the derivative of the sine function is the cosine function. Thanks for watching. Please consider subscribing.